Hello all. This is the week 7 of uh, Digital Circuits tutorial. The course is offered by Professor Shantanu Chattopadhyay. Myself, I am Sai Shubham and I am in my PhD second year. I am pursuing electrical engineering PhD in from IIT Gandhinagar. Okay, so let's start today's tutorial. So this is the first question. If it is not visible, this is actually logic 1. Right? So the question says, assume initial contents of all D flip-flops are reset to logic 0. The serial input is tied to logic 1. What are the contents of the register after 3 clock cycles? So the question is basically asking, suppose this is node Q0, Q1, Q2 and Q3. So this Q0, Q1, Q2, Q3 are set to 0 initially, and the question asks what will be the value of Q0, Q1, Q2, Q3 after 3 clock cycles. Okay, so I will give you about 5 minutes to solve this question. So the thing to keep in mind is that this is a D flip-flop. I will give you a hint. This is a D flip-flop. So in D flip-flop, what happens is that whenever there is a clock edge, like whenever there is a transition of clock from 0 to 1, Q is basically D. Whatever data is stored in D is transferred to Q directly. Okay. So today the topics that I am going to cover are basic flops questions and some counters, finite state machines, and probably I will uh, cover some topics of static time analysis. Okay. So I will give you 1 more minute and then I will provide the solution. I think this is a pretty easy question. Let's discuss the solution now. So let's write Q0, Q1, Q2, Q3. Okay. So since the serial input is 1, this is D, this is 1, and initially they all were 0. Now this one will appear over here. So the output will be somewhat like this. And these values will shift, okay? So after 3 cycles, this is first cycle, second and third, okay? So after 3 cycles, this is the answer, okay? So the answer is 1110, option B. Fine. Moving on to the next question. So the contents of the following register, Q3, Q2, Q1, Q0, after 3 clock transitions are. So the initial states of the flops, the output of the flops is given 1001. You have to find out after 3 clock transitions what will be the output. There is a follow-up question. Also find the output, that is the Q3 value. Okay, so what will be the series? So I will give you about 5 minutes to solve this question. So I hope the question is clear. The first part of the question is to find out Q0, Q1, Q2, Q3 after 3 clock transition, and the second is that to find the output, which is basically Q3. So how will the pattern follow? So so I will discuss the solution now. So you can see that D naught is basically Q2 XOR of Q2 and Q3, and whatever there is whatever the value there is in Q naught, it will be transferred into D1. Q1 value will be transferred into D2, and Q2 will be transferred into D3. Okay. So we will write Q1, Q2, Q3, Q4, fine, and D naught, which is basically XOR Q3, Q2. Okay. So initial conditions are given 1 0 0 1. So initial conditions 1 0 0 1, and D naught will be XOR of, okay, I think I made a mistake in numbering. Q0, Q1, Q2, Q3. So D naught is XOR of Q2 and Q3. So D naught is 1. So this one will be reflected in the next cycle. Okay. So then output will be 1. This one will come here. 0 will come here. 0. Okay. Now the XOR of 0 and 0. This is 0. Next cycle 0, 1, 1, 0. The XOR will be 1. Next cycle 1, 0, 1, 1. And the XOR will be 0. Okay. So how many cycles? I think this is the third cycle. This is first. This is second. And this is the third cycle. Okay. So the output is, so they are asking Q3, Q2, Q1, Q0. That will be 1101. Okay. So 1101. So this is the answer. Regarding the pattern of Q3, this is Q3 pattern is 1001. So we have two options over here, A and D. Okay. So we have to do for few more cycles. So the pattern of Q3 is 100110, which is option A. Okay. So answer question 2, D and A. Fine. So let's move on to the next question. So what is the mod value of a 4-bit twisted ring counter? To give you a hint, uh, twisted ring counter is basically a Johnson counter. Okay. Mod value is basically number of unique output states. So if you are done with this question, you might try to attempt what is the mod value of a 4-bit ring counter, simple ring counter. So I am discussing the solution right now. A Johnson counter, 4-bit Johnson counter is, suppose there are 4 flops connected to each other, connected serially, and the knot of this last flop is fed to the D of the first flip flop. So this is the Johnson counter. So suppose uh, the initial states are 0 0 0 0, then the Johnson counter will work like, because this 0, this is 0, so this is 1, so this one will be fed in the fed to the first flop. Okay, so this is appearing over here. Fine. Similarly, this will be the pattern. So these are the, and then it will go to the previous state. Okay, to the first state. So the number of independent output states are 8. Okay, so the mod value of the 4-bit twisted ring counter, so 4-bit twisted ring counter is basically equal to 4-bit Johnson counter. Okay, so the mod value is 8. Okay, so option B. So another question is, what is the mod value of a 4-bit ring counter? This is a simple ring counter. Okay, I think this can be easily done. So this is similar to the previous question. A 4-bit ring counter will have a pattern like this. If the states are 1 0 0 0, then it will come here 0 1 0 0, and this 0 will come in this position 0 0 1 0 0 0 0 1 and 1 0 0 0. So this way it will repeat. Fine. So this is a ring counter. So the number of unique output states are 4. So the mod value is 4. So this answer is B. Okay. So some of you were asking for the slides. So I have uploaded all the slides from week 1 to week 6. Okay. And I have shared the drive link as well. So the next question is, what is the output frequency of the following circuit for 10 megahertz clock signal? So there are two questions. So I will discuss the solution in 3 minutes. So the hint that I will give you is that hint is that for a JK flip-flop, if J equal to 1 and K equal to 1, so Qn plus 1 will be Qn bar. Fine. So I will discuss the solution now. Suppose J is 1 and K is 1. We will write the clock patterns 0, 1, 0, 1. Fine. So the pauses are these points. Suppose the initial value of the clock was, the initial value of the output was 0. So at the clock edge, it will toggle to 1. And it will remain at 1 as long as it finds the next pauses. Okay. So after this point, it will be 0 again, then it will be 1, then it will be 0 again and 1. Okay. So what you can see is that it's taking double the time as compared to the clock. So time period Jk is equal to 2 times time period of clock, which means frequency of Jk is half clock frequency, which is 10 by 2 equal to 5 megahertz. Okay, so that is the answer. Now the follow-up question is that what is the frequency when J equal to K equal to 0? So the only way you can solve this question is when you are aware about the truth table of the JK flip-flop. Okay. So in a JK flip-flop, whenever you have a pause edge, if J is 0, K is 0, then Qn is basically Qn minus 1 because it acts as a memory. If you have 0, 1, then output will be 0. If you have 1, 0, the output will be 1. And if you have 1, 1, it will be Qn minus 1 bar. Okay. So in the previous question, this concept was utilized, and toggle is important for clock because it has to continuously oscillate from 0 and 1. Okay. In this case, it acts as a memory, so it won't change state. So it will have no frequency, right? So answer is C, 0 megahertz. Okay. So moving on to the next question. The initial contents of the following flip-flops are 0, 1, 1, 0. What are the contents after 2 clock cycles? This is also a very straightforward question, and I think this is similar to a Johnson counter. I will discuss the solution now. I hope you could solve it. So A, B, C, D, there is no D, E and E bar. Okay. So initially this is 0, 1, 1, 0, E bar is 1, and this E bar is fed to A. Okay. So in the next iteration it will be 1, 0, 1, 1. In the second iteration it is 0, 1, 0, 1. So the answer is option B, 0, 1, 0, 1. Okay. Next question. I think the figure is clearly visible. This is Q0, this is Q1, this is Q2, this is Q3. Okay. So which of the following statement is true for the given circuit? So I will give you 3 more minutes to think. The question is very straightforward. Since I explained you Johnson counter, where the bar of the last clock will be fed to the first clock. So since this circuit is not similar to Johnson counter circuit, so this is not a Johnson ring counter. So option C is not the case. As you can see, the same clock is fed to all the flops. Okay. So as we know, in case of a synchronous circuit, there is a single clock which is fed to all the clocks, right? So this is not a asynchronous circuit, which means option A and option D are incorrect, which implies that option B is the correct answer. Okay. In fact, you can uh, we can make the outputs as well. So initially, suppose they all are 1. Okay. Now, this Q1, this Q0 will go to 0. Since Q0 was 1, Q1 will also toggle. So this will be 0, this will be 0, and this will be 0. Fine. Then so I'm currently explaining how it behaves as a 4-bit synchronous up counter. Okay. So the input is always high. So since the input is high, Q0 will continue to toggle. Now, this is the case. Then it will again be 1. Previous states will continue. Since this is 1, this will toggle. Okay, so this will be 1. And since this is always 1, this will be 0. So 1, 1, 0, 0. And now since this is 1, this will toggle this one. So this will be 0. This will be 0. And since these both are 1, you can see that when Q0, Q1 both are 1, J2 will be 1. So in that case, what will happen is that Q2 will also toggle, and since it was initially 0, it will be 1. Okay. So you can see the pattern. Q0, Q1, Q3, Q2, Q1, Q0. The pattern is like 1, 1, 1, 1, 0, 0, 0, 0. So it is clearly behaving as a synchronous up counter. Okay. So now moving on to the next question. For the circuit shown, the clock frequency is F0 and the duty cycle is 25% for the signal at the Q output of the flip-flop. We have to figure out the frequency and the duty cycle. So I will give you about 5 minutes to do this problem. This is a slightly difficult problem. Actually, you might have to check again. The correct answer is A.
Frequency is actually divided by 2, sir. F naught by 2.
Okay, f naught by 2.
And
Okay, I have
cycle
also made, sorry, duty cycle.
duty cycle is 50%. And frequency is F naught by 2. So answer C is C may be correct.
Okay, we will see. Actually, I have also made the solution, but it is coming out to be f naught by 4 and the duty cycle is 50%. So when I will show the solution, if there is a mistake, free feel to point it out, okay? So I think I should start with the solution. So this is the input clock. Duty cycle is 25%. Okay. Now, so this input clock is fed to a 2-bit binary counter. Okay. So we have LSB, MSB. So whenever the clock is 1, MSB is high. I will show you. It's something like this. So whenever 1 appears, the 2-bit binary counter is updated. So this will be 1 0. This will continue to be 1 for all these 5, and then it will be toggled. So 0 1. Then you will have 1 1 1 1 1 1 1. Okay. Now this LSB is fed to JK. Okay. So let's separate out the LSB part. So this is equal to J. Now Q, if you look at Q, so whenever there is 1, it will toggle, right? So in that case, suppose initially the Q is 1. For example, initially it is 1. Now, as soon as you have J as 1, it will toggle, right? J equal to K. Okay. So it will toggle. It will toggle till the point, till the next 1 appears. Fine. Sorry, it will remain the same till the next 1 appears, and then it will toggle again. So you can see that this 0 is for about, suppose this time we consider t, so 0 is for 8t, 1 is for 8t, so the total cycle is 16t. Okay. If you look at the clock, this one block was t, so the time period of clock is 4t. because after 4 blocks it repeats. So you can see that since this queue is taking 4 times more time, 4x more time, frequency equal to f naught by 4, and duty cycle is 50%. Duty cycle is 50% because the duration for which the 0 is there, for the same duration 1 is there. Okay, so uh, is the doubt clear? I think someone said that the frequency is coming out to be f naught by 2. So is it clear to you? I hope this is clear. I will move on to the next question. So what is the sequence QA, QB, QC produced by the below circuit, assuming the initial condition 1, 1, 1? This is a straightforward question. I will give you 2 minutes to solve. I think I will discuss the solution now. Okay, this is a straightforward question. So you can see that DA, so there is QA, QB, QC, and DA, which is XOR of QA, QC, and this DA will be the next QA n plus 1. Fine. Now, mm, so the initial conditions are 1, 1, 1. So DA will be XOR of QA, QC, XOR 1 and 1, which is 0. So next will be 0, 1, 1. Then XOR of 1 and 0, will be 1. So next iteration will be 1 0 1. So as you can see, 1 1 1 0 1 1 1 0 1. This is similar to option B. So option B is the answer. Fine. I hope this is clear. I'm moving on to the next question. Identify the outputs of the following circuit after 6 clock transitions. The initial value of the flip-flops are 0. So by initial value, they are talking about the values of Q. Okay. So all Q0, Q1, Q2, Q3 are 0. So I will give you about 4 minutes to solve this question. I think I should discuss the solution now. Okay. So if you look here, Q, Q bar, and D for the next cycle. So supposing there is a clock edge over here, how are these values going to change? So what are the initial conditions? All flops are 0, uh, which means Q is 0, Q bar is 1 and D is 1. So this D will be reflected in the next cycle. So this will be 1, Q bar will be 0 and D will be 0. Okay. So the cycle will look something like this. Fine. So this is for the FF0. Now what about FF1? So if you look, Q bar is basically being fed to the clock of FF1, right? So the clock for FF1 looks like this. So these are the edges. So your edge lies here, positive edge. Now let's look again at Q bar, D. So in this case, this is 0, 1, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1. Fine. So there is a pattern. So if you do it for Q0, Q1, Q2, Q3, the pattern that will come is something like this. Okay. So what is the question? The question is Q3, Q2, Q1, Q0 after the 6th cycle. So this is after the first cycle. This is first, second, third, fourth, fifth, and sixth. So the answer is 0, 1, 1, 0. Okay. So the next question. In the given sequential circuit, initial states are Q1 equal to 1, Q2 equal to 0 for a clock frequency of 4 MHz. The frequency of the signal Q1 in kilohertz is. So this is a simple question. I will give you a couple of minutes to solve. So I think I will discuss the solution now. So if you see, Q1 equal to 1 and Q2 equal to 0. Q1 D1, Q1 bar D2, Q2. Okay. So it's asking frequency of Q1. So now Q1 is 1, Q1 bar is 0, D2 given is 0, sorry, Q2 given is 0. Since Q1 bar and D2 are short, so this will be 0. Q2 and D2 are connected. Q2 and D1 are connected, so this has to be 0. Okay. So in the next iteration, what will happen? In the next iteration, since D1 is 0, this will be Q1. Fine. And Q1 bar will be 1. This will be D2 will be 1. This 0 will come here. So this is 0. This is 0. Now again, this 0 will come here. So 0. Q1 bar will be 1. 1. And this 1 will come over here. Okay. This one will appear over here. Q1 bar is 0, 0, 1, 1. 1, 0, 0, 0, 0. Okay. So what you have seen is that now it repeats itself. Okay. Now it repeats itself. So what will be the frequency? So we know that for this transition, the clock had to give a pause edge. So there was 0, 1 for this. For this transition as well, you had 0, 1, 0, 1 and 0, 1. Okay. So the total clock transitions it took was, suppose 0 is there for t time. Okay. So total transitions are 8t and clock transition is 2t. Okay. So for Q it is 8t. So the frequency, you can see that this is 4 times. So frequency is 4 megahertz by 4 equal to 1 megahertz equal to 1000 kilohertz. So option A. So option A is the answer. Fine. Moving on to the next question. Which of the following? So I hope this was clear to everyone. Moving on to the next question. Which of the following can be designed using a shift register? So the correct answer is option A. So shift. Um, in asynchronous up counter and down counter, you will be needing other logic gates as well to make the circuit. Whereas in ring counter, you can directly do it because in ring counter, suppose these are the initial states, you have to basically shift the value of 0 to the previous flop. So it will be like this. So this can be done using a shift register. So option A is the answer. The next question says, which of the following statement is true? In synchronous counter, we use a universal clock that is common to all flip-flops. In asynchronous counter, we use a universal clock that is common to all flip-flops. And option C says, in synchronous counter, the main clock is only applied to the first flop, and then for the rest of the flops, the output of the previous flop is taken as a clock. So the correct answer is option A. So in synchronous counter, all the flops will have a same universal clock. Option B is wrong because option B says that the universal clock is fed to all the flip-flops, which is not the case. In asynchronous counter, the main clock is fed to the first flop and rest of the clocks. So in rest of the flops, flip-flops, the output of the previous flop is used as a clock. So in this case, as you can see, to this statement, if I make the synchronous counter as asynchronous, this option will be correct. So option A is the correct answer. Let me explain again. So in the option C, the definition is given for the asynchronous counter instead of a synchronous counter. Moving on to the next question. Which of the following statements is true? In Moore and Mealy machine, output does not depend on input. Moore and Mealy machine, output depends on input. Moore and Mealy machine, output depends on the current state. And option D, Moore and Mealy machine output depends on both input and current state.
Option C is correct. Option C.
Yeah. So option C is the correct answer. So in Moore machine, the inputs update the state which gives the output. In Mealy machine, input update the state and the input and the new state and the input both go into some logic which gives the correct output. So option C says that Moore and Millie machine output depends on the current state, which is true. So this instant is your current state. This is your current state. So in both the machines, you can see that it is dependent on the current state. Option A says that Moore and Millie machine output does not depend on the input. In Millie machine, it depends. Moore and Millie machine output depends on the input. So you can see that in Moore machine, the state is updated using the input, but the output is dependent on the state. So option B is incorrect. And in option D, this is the definition for Millie machine, not Moore machine. Okay. So I think I will come back to this question later. So this is another question regarding finite state machines. The following is a finite state machine diagram for a 1100 detector. Okay. So what should be the values of A, B, C, D, E, where these are outputs of the FSM? So you might have made FSM for different kind of operations. So in this case, we are making FSM for 1100 detector. So it means that, let me explain. There is some input, output and input. Okay. So suppose the input is like 001, 01, 1001. So in that case, what will happen? The output will always be 0. And as soon as it detects 1100 pattern, it should give the output as 1. And again, it will give 0. Okay. So this is a finite state machine for 1100 detector. So you have to find out the values of A, B, C, D, E. So A, B, C, D, E are basically the output. Okay. Suppose my present state is A and I provided the input as 1. So it went to state B. So corresponding to state B, there will be some output. Okay. This output. So you have to figure out what is that. So finite state machines are also a standard interview questions. So any digital electronics company you go, they will always ask you to make a FSM, and the questions will be like, make an FSM for suppose 1100 detector or 1001 detector. So in 1001, there are two cases. One is like, this is my 1001 pattern. Okay. So 1001, 1001. Another case can be, so this is also my 1001 pattern, 1001, and there is also 1001. So this one is common to both. So this is called as non-overlapping. This is overlapping. Okay. So in the interview, they will ask you to make either Moore machine or Millie machine for non-overlap or overlap cases. Okay. For a sequence detector. So this is basically a sequence detector. So can you give it a try? Like, what can be the value of A, B, C, D, E? So Harsha, not exactly this is the case. Uh, what I am asking is that whenever, suppose this is my present state, okay? So whenever the output is, so whenever the input is 1, I move on to the next state B. So corresponding to B, there will be some output, right? So it will be a single output. For example, suppose this is state A, okay? This is state A. Now I got an input as 1. So I move to this state, which is B. So corresponding to A, the output was 0. Corresponding to B, the output was also 0. So this is what I'm asking. So in you can see that A, B, C, D, E, there are 4 outputs. So one of them can only be 1 and rest of them will be 0. If the question is not clear, please ask. So let me show you an example. So I am making a Moore machine that detects 1. So the output will be 0 whenever the input is 0. Now, as soon as I give input as 1, the machine detects that it is 1. So the output will be 1. Now, here, whenever the input is 1, it will continue to give this output as 1. But as soon as in this state, if you give 0, it will go back to the previous state and the output will be 0 again. So suppose this is A and this is B. So what I am asking is that the value of this state is 0 and the value of this state is 1. Okay. So this is a very simplified example. This is a 1 detector. Okay. So similar to this, you have to figure out the value of ABCDE. It will be only 1 bit.
Sir, but A, B, C, D, E are the states.
No, ABCDE are states, but what I am asking is the output corresponding to that state.
Okay, okay.
So suppose you reached A, so there will be some output, right, of the Moore machine. So that is what I am asking.
Okay. So A is 0, B is 0, C is 0, D is 0, and E is 1.
Yeah, that is correct. So if you plug, so you can see that the pattern is there 1, 1, 0, and 0. So as soon as the 1, 1, 0 pattern is completed, I think it is visible 0, 0. So as soon as that pattern is completed, the 1 is displayed. Okay. And after that, whatever input you give, it will go back to the 0 output. Fine. So moving on to the next question. The following is a, 1 second, it's, so the following is a finite state machine diagram for 1100 detector, same, but instead of a Moore machine, this is a Mealy machine. Fine. So here, instead of having an output corresponding to state, we have this as input and this as output. Okay. So you can see that some outputs are missing, A, B, C, D, E. So you have to tell me what is the value of A, B, C, D, E. So one of them will be output 1 and others will be 0. So the correct answer is, I will discuss. So this will be 1 and rest of them will be 0. So the easy trick is that this will be the final state. The reason being is that as you go towards the final state, it has less number of arrows and the previous states will have more arrows pointing to them. So these will be the initial states and this is the final state. So what you can see is that there is 1100 pattern. So 1, 1, 0 and 0 pattern. So as soon as there is input 0, the output is 1. Okay. Triple 101. Actually, it cannot be 11101. The reason is that 11101 you said, it means that the output is 1 most of the time, which implies that the pattern 1, what was the pattern 1100 is correct, right? So which is not the case. Okay, fine, 1000. So I have one more question to discuss with you. I think this is the question. So what should be the minimum time period of the clock so that there is no timing violation? So For those who are not very much sure about this, I will explain right now. So for a flop, so I am just explaining the concept behind it. Then I will ask you to solve this question. Okay. So whenever the flop is there, and you have a clock edge, right? This is a clock, and flop is positively edge triggered. So this is the posage of the clock. So you want your data D to be available before the posage. Okay, so that this data can be directly latched to the output. So our output will be somewhat like this. Okay, since this is 1, so the output is 1. So what you want is that this T should be present at the clock edge for a certain time before the posage. Okay, and the same data should be available after the posage as well for a particular amount of time. So this minimum time for which, so minimum time after posage is your hold time or TH. Minimum time before posage is your setup time, which is TS. Okay, so this is the requirement of every flip flop. If it violates this, then your circuit may not work because it will move on to some metastable condition. So metastability in a flip flop is that the data is not properly latched. For example, let's take this case only. This is your clock. Okay, and your data D is available here. Okay, and your setup time was this much. So even though this is 1 before clock edge, we cannot guarantee that the output will be 1. Fine. Similarly, if your data is 1 throughout, but right before your hold time, it goes down to 0. Okay. So this is your hold time requirement. This one. So it was initially 1. So the setup requirement is fulfilled. But the violation happens here because it goes down from 1 to 0 just before the hold time. So in that case also, this is your data D. So in this case, in both the cases Q, we can't say. It can either be 1 or 0. So the requirement of this question is that, so this is known as timing violation. Okay. So the requirement for this question is that what should be the time period of the clock so that there is no timing violation. So is the question clear? I think I can give you a little more explanation in this question. So this is clock 1, this is clock 2. Okay, this is your main clock. So it will appear something like this. If you make a waveform, so clock 1, So clock 1 will have some delay because there is some path delay. Okay. So right now it will take some time. Then it will go up. Clock 2 has much bigger delay. Okay. So it will take more time. Fine. Now one second. So now I have D. Okay. This requirement, and this D is what we are talking about is this D. Okay. We know that this is already available. Already available. Okay. So clock 1, clock 2, fine. It will have some time period T. So your data D. So the condition with data D is that this is not time period actually. This is time period. So the condition with data D is that it comes from flop 1 and it has to go through a combinational block and then it has to go to flop 2. Okay. So it can come out of flop 1 after this clock edge and it should be available before the setup time here. So this is what you have to check. Another condition that you have to check is that this is case 1. Another case that you have to check is that I think this is clear, right? The data came out from flop 1. It has to go to flop 2. Okay. But the data should be available before the setup time. So this is clock 2. This is clock 2. And this is the setup time requirement. Okay. So data should be available before that. Another thing is that you have to check that data should not be available right here because in this edge you have a hold time requirement. Okay. So the data should not change here at this point. So these are the two conditions that you have to check. This is known as setup time requirement that you have to check. This is hold time. Okay. So I hope this question is clear. Can you give this a try? If the question is not clear, let me know. I will explain again. But this is a very important question with respect to interviews because this topic is known as static timing analysis and they ask in every interview in the for digital electronics company. Yes, that is correct. D for case 1 is 18 nanoseconds. So you need to figure out that uh, So 18 nanosecond is the minimum time, right? And the clock should also reach there. So you have to make sure that the clock reaches before the data. Then only you will avoid the hold violation. Because the clock edge appeared, and after that, if the data suddenly changes inside the hold boundary, then you will have a violation, right? So for hold case, you have to check. So for the hold case, uh, data is coming faster and the clock is slow. In setup case, data is slow and the clock is fast. 26 nanosecond. So are you talking about a time period? That is not the correct answer. So that is actually the answer, but I am talking about the minimum time period. Okay. So for the following circuit that I've shown, if you give the time period as 26 nanosecond, it will work perfectly fine without any violation. But the time period is big, right? And we want our processing to be faster. So you are actually going in the right direction. So maybe you can take hint from here. So when we are talking about hold time, what we are saying is that the data should not travel from from flop 1 to flop 2 in the same cycle. Suppose what I'm saying is that what should not happen is that the available data, suppose this is D1. So what should not happen is that D1 should be available at the output of flop 2 at the same clock edge. So that we have to avoid. So in the first clock edge, D1 should be available after flop 1. In the second clock edge, it should be available after flop 2. So in the hold violation, what happens is that data D1 is present after the flop 2 uh, because there is no enough like enough delay between the flops. So the answer is that the time period should be more than 21 nanosecond. So if you can figure it out. So are you still trying, or should I explain the solution?
Explain, sir.
Yeah. So in the above circuit, what we can do is that we can club the minimum and maximum time together. Okay. Like this is minimum 1 nanosecond, 6 nanosecond. So we can club them together. Okay. So if you do that, the circuit will 1 second. Yeah. So I am explaining the solution. So if we club all the minimum time and maximum time together, the circuit will look something like this. Okay. This is flop 1. There is some combinational logic that has delay. This is flop 2. There is clock. There is also some delay over here. This is the main clock. There is another delay. This is fed to this flop. TH is hold time is 2. Setup time is 4. Now this is the minimum time. This is the maximum time for a flop. For this part, it is 8 nanoseconds and 13 nanoseconds. Okay. For this path, it is 9 and 15. For this, it is 1 and 2. Okay. So, including the flop and all the path, if the data D has to go through the flop 1 and reach at flop 2. Okay. So, this is your Q value. Q equal to dt. So, the entire will be from 17 nanoseconds to 24 nanoseconds. Fine. So let's make a timing diagram. So this is clock. Suppose there is a positive edge. Okay. So what about clock 1? 1 second. Clock 1. It will have some delay. Why delay? Because this is your clock 1 and this is your clock 2. So clock 1 will have this much delay, clock 2 will have this much delay. Fine. So this is clock 1 and so we are checking setup and hold violation at flop 2. Okay. So this delay is 1 comma 2. Similarly, this delay is 9 comma 15. So 9 is the minimum time and 15 is the maximum time. So yeah. This is the time period T. Okay. Let's look at data D. So first requirement is that the data D should not appear immediately after this clock edge. Okay. This clock edge. It should not immediately appear. The reason is that it can violate the setup time. Okay, so it can violate the setup time. So data D will appear after this clock edge. Fine. So from this clock edge, it will take how much time? 17 to 24. So this is 17 comma 24. Okay, so we have to check for that. Okay, this is your hold time, T hold. So our requirement is that 1 comma 2 plus 17 comma 24. Let me try it again. This is 1 comma 2. So 1 comma 2 plus 17 comma 24 should be always greater than 9 comma 15 plus T hold, because if this data transition falls within this hold margin, then it will cause some problem, right? It will cause metastability. So we want D to change as ahead as possible. Okay, so this is a better scenario. Fine. So if we solve this, so if you look at this expression, right, so we have to always consider the worst case, because if you take the maximum value 2 plus 24 greater than 9 plus setup time is hold time is 2, so this will always be this will sometimes be correct, right? Sometimes correct. We want always correct. Consider, for that we have to consider worst case. Okay, so for this expression, if this part 1 comma 2 plus 17 comma 24 has to be greater than 9 comma 15 plus th, then this part has to be what? As minimum as possible, and this part has to be maximum as possible. Then only it will be a worst case, right? If we take the maximum of this part, then it will always be greater than this part, right? The right hand side part, RHS. But that we don't want. We want the worst case scenario. So for that we will take the minimum value. So for minimum value it will be 2 plus 24. Sorry, it's not 2 plus 24. It's 1 plus 17. Okay, should be greater than. We will take the maximum value here. So it will be 15 plus 2. So 18 greater than 17, which means what? The relation holds true in worst case. Therefore, no hold violation. Fine. Now let's move. So this is clear, right? Till now, that there is no hold violation. So moving on to the next part. What we also do not want is that for the flop 2, there is some setup time, TS. So what we do not want is that this data D should appear at this window. Okay, that we do not want. So our condition is like this. So this is our condition. Okay, this is 1 comma 2 and this is our 17 comma 24, suppose. So if you look closely, what do we have here? We can write this part. We have to subtract setup time from okay, let me copy this again. So if you look here, what is this distance? This is 1 comma 2 plus, we actually do not need 1 comma 2, 9 comma 15 plus, this is 9 comma 15. Okay, 9 comma 15 plus time period minus t setup. Okay, so this is the green part. Now the data part is 1 comma 2 plus 17 comma 24. So this should always be less than your green part, then there is no violation. Okay, so now we will apply the same logic. If this has to be greater, then we have to take the minimum of it and we have to take the maximum of it. Okay, so here if we take the maximum, it will be 2 plus 24 less than 9 plus t minus setup time is 4. So 26 less than 5 plus t. So I think you reached about reached at this stage of the solution. So you almost got 26 nanosecond, but the correct answer is that t greater than 21 nanoseconds. So this is how you get your time period. Okay, so if you maintain this time, then no setup violation. Okay, so is this clear? If you want me to explain any part, you can ask. So that's all for today's tutorial. I am stopping the recording right now. If you have anything to ask, you can go ahead.